To wrap up today, let's talk about the runtime for left-leaning red-black tree operations and their implementation, and then we'll summarize. So it turns out that the runtime analysis for our left-leaning red-black trees is very simple if you trust the 2-3 tree runtime. Because we have a tree which is structurally identical to the 2-3 tree, we know that our LLRB tree has height, which is big O of log n. So contains is trivially big O of log n because we simply need to search the tree like we usually would. And insert, we have to do a little more thinking. So first of all, we have to add the new node, and that's exactly like a regular BST. And then we have some rotation and color flip operations, and it's going to be big O of log n of those operations. Because at worst, you have to do an operation each level of the tree going up. So you'll do one maybe at the leaf, and then one up, one up, one up, one up, and so forth. And since rotations and color flips are constant time operations, the overall runtime is also log n. Now we're not going to talk about LLRB delete. It's not because it's necessarily super crazy. I mean, it is more complicated than insertion, but it's just not interesting enough for us to talk about in great detail. So if you'd like, go look at the 2-3 tree lecture, the optional slides that were there for the deletion operation and the LLRB deletion operations. You actually might find it interesting to try and rederive them. But be aware, it's a long road, but you might find it fun. Okay, so runtime turns out to be pretty simple. And so what we get out of this is that unlike our regular binary search trees, we now get log performance. But unlike a 2-3 tree, it is much easier to implement. So somewhat surprisingly, turning a binary search tree into a left-leaning red-black binary search tree, which is balanced, only takes 3 extra lines of code that are clever. So in particular, this is straight from the optional textbook for our course. The put method for a red-black tree has 3 extra lines. The first is, if you have a red right child and your left child is not red, then you rotate to the left, as we said earlier. If you have a red left child and a red grand left child, we rotate to the right. And if we have a left red and a left right child, well, then we flip the colors of our current node. And in that way, if you write these helper methods, it turns out they're not actually that interesting or deep. If you have these helper methods around, you just need these 3 lines of code, and you get a nice balanced tree. Now here in this course, I'm focusing only on the conceptual picture. You can try and implement this, but it's just a little too much implementation detail for us to make into like a major homework or something. But be aware that it is possible to implement this in only a few lines of code, but the important part is the ideas. All right, so to summarize search trees. So in the last 3 lectures, we've talked about using search trees to implement sets and maps. We had binary search trees, which were simple, but can get imbalanced. We had 2-3 trees, which were balanced, but they're annoying to implement, and they're relatively slow compared to other possibilities. Then we introduced the left-leaning red-black tree, which is simple to implement, although the delete can be a little hard. And it works by maintaining this one-to-one correspondence or bijection with a 2-3 tree. And then Java's TreeMap, I should mention, it is a red-black tree. It uses the same idea that we've been doing. So if you click here, you can go look at the actual code, and you can see that it has, for example, once this loads, we'll have like rotate. So it has these rotate left and rotate right operations. It tries and checks colors. So this is real stuff. This is what the Java library uses. Now, unlike what we did, it's instead of a correspondence to a 2-3 tree, it's correspondence with a 2-3-4 tree. And there's a little more play there's not a unique representation. So it happens to be not a one-to-one correspondence, but it's still a representation in the same way. And the key difference is that it allows glue links on either side. And that gives, if you want, you can read the Wikipedia article, which gives a high-level picture. Now, it's a more complex implementation, but it seems to be, as far as I understand, given things I have read, but I've never done a deep analysis myself, that these are significantly faster than the left-leaning variety, but at the cost of some more complexity. So we're not going to go into this approach just because I don't think it's that much different. It's just more stuff to try and cram into your brain. And to conclude today, I should say that there are other ways of doing things. I've only shown you this narrative, how we get from a basic binary search tree to the way that it's done in the Java libraries. But there's other approaches. There's, for example, something known as an AVL tree. There are splay trees. There's treeps. And in fact, other ideas out there. There are many other types of trees which are self-balancing in some way. And some of them are on average balanced, guaranteed balanced. There's, tons of these. And it's a product of the fact that there's a lot of people out there who had to write PhDs, or people who just found it interesting to try and pursue this line of research and see what they could come up with. But it seems that the red-black tree is one of the best overall. So that's what people seem to actually use. And I should note also, there are entirely different ways to implement sets and maps. So instead of using a search tree, you could use the skip list, which we mentioned at the beginning of the balanced search tree lecture, for example. In that case, that one relies on randomness instead of structure that is balanced. And then there's other ideas entirely that have nothing to do with either lists or trees. And so hashing is going to be the most common alternative. And this is what we're going to be discussing in our next lecture. All right, so that's it for today. I hope you found that interesting. It's a pretty deep lecture, but I think it's a cool narrative that ties this all together, that if we want a balanced search tree, then we can rely on this cool one-to-one correspondence with a different type of search tree. This is really neat stuff to me, so I hope you enjoyed, and I'll see you next time.